Welcome to Topic 4, Ice Caps. What are they and why are they important for us to study? 97% of the ice on Earth is locked up in the ice sheets, so the remaining 3%, covering an area of 500,000 kilometers squared, exists as ice caps, ice fields and glaciers located at high latitudes or in mountainous regions around the world. In this topic, we distinguish between ice fields and ice caps. We can describe ice fields as being ice masses where the flow is influenced predominantly by topography, and unlike an ice cap, they do not have a dome-like surface. Ice fields fall under the category of mountain glaciers covered earlier in the course, so now we will focus on ice caps. Just like ice sheets, ice caps submerge the landscape, at least in their central portion, and major patterns of ice flow are largely independent of undulations in the bed. Remember, ice flow is dominated by the driving stress, which is dependent upon the surface slope. As we have seen with outlet glaciers and ice streams at the margins, they are more commonly located in topographic depressions. So, it is the ice mass that we use to distinguish between ice cap and ice sheet. An ice sheet is 50,000 kilometers squared or more, so any ice dome mass of ice smaller than 50,000 kilometers squared that has glacier flow from the divides is classed as an ice cap. The largest contemporary ice masses, which we define as ice caps, are found in Svalbard, Ellesmere Island, Baffin Island and Iceland, so mostly located in the Northern Hemisphere. So now we know what an ice cap is. Why are they important for us to study? Well, ice caps play an important role in the climate system through key interactions and feedbacks at global scales. For example, albedo and ocean circulation. Ice caps are also important because they react relatively quickly to climate effects, influencing ecosystems and human activities on a local scale. We've already said that ice caps are located mostly in the Northern Hemisphere, and there are also populations and communities in these areas. The fact that they react relatively quickly also means they're a good indicator of change, and timescales and sensitivity is something we will return to. But probably most pressing, for a global concern, is sea level rise. We know that it's caused primarily by two factors related to global warming: the added water from melting of ice sheets and glaciers, and the expansion of seawater as it warms. So let's recap the sea level potential of the ice sheets and the ice masses on Earth. At the top of the page is the National Snow and Ice Data Centre, a quote from there, that if all the land ice melted, sea level would rise by approximately 70 metres. So that's the total sea level potential of the cryosphere. Let's recap the ice sheets. So we know terrestrially based Greenland, if that all melted, would contribute 7 metres to sea level rise. The East Antarctic ice sheet is an order of magnitude bigger, 53.3 metres sea level rise potential. The marine-based West Antarctic ice sheet, since it already sits below sea level and has already offset some of the displaced some of the water surrounding it, is much less, only 4.3 metres sea level rise, but still significant, and it's unstable. So together, for Antarctica, we're looking at 58 metres. We've got Greenland of 7 metres, so that only leaves about 5 metres or so sea level potential for all the remaining ice on Earth, which includes mountain glaciers, ice fields, and ice caps. So if you break it down further into just ice caps, then they're only a very small percentage of sea level rise potential. However, these numbers are only potentials. That is not to say this is the ice is going to melt and this is how much sea level rise is going to take place. This is just how much ice is locked up in these ice masses. So far more important than potential is sensitivity of these ice masses. How likely are they to melt, and over what timescales? And this is really important for ice caps, which show much more sensitivity to the ice sheets. So let's return to the IPCC Special Report on Oceans and Cryosphere to look into the contributions of sea level rise from the ice sheets and ice caps from between 2006 and 2015. So let's look at Greenland. The ice sheet lost an average of 278 gigatons per year, so that's equivalent of 0.77 millimeters per year during that time period. And as you extend it further, you can see from this graph that from where we are here, these are projections based on the scenario 8.5 and also the 2.6, with the uncertainty shown by the boxes. So for Greenland, between 2006 and 2015, let's compare that to Antarctica, which had mass loss at an average rate of 155 gigatons per year, mostly due to rapid thinning and retreat of major outlet glaciers draining the West Antarctic ice sheet. The glaciers worldwide, outside of Greenland and Antarctica, they lost an average rate of 220 gigatons per year. That's equivalent to 0.61 millimeters a year sea level rise. So it's right up there with the ice sheets. We can see that the rest of the glacier mass loss outside of the ice sheets is significant and making a big contribution to sea level rise right now. We also know that the cryosphere, which is an area covered by ice, snow, glaciers and permafrost, is an extremely dynamic part of our global system. Changes in seasons and climate bring great changes to the Earth's cryosphere. And so we need to take into account any changes in, say, the North Atlantic shift or pressure systems, or we've seen the influence of ocean currents on Jakobshavn and Isbrae. Well, what are the influence of such multi-decadal oscillations on ice caps, and how is this likely to change in the future?